Last time we finished with gravitational potential energy. This is one tool that we're going to use a bunch when using energy. I told you last time that work total is equal to the change in kinetic energy. But there's other kinds of energy that we can deal with, like the work due to gravitational forces. Gravity does work on stuff. Springs do work on stuff. See that it actually says work springs right there? But I crossed it off because we haven't talked about springs yet. But that can be a form of work. And then other things can be a form of work. And all that equals the change in kinetic energy. But we determined that the work due to gravity is equal to the negative of the change of the gravitational potential. And so if we are ignoring springs, pretend we have no idea what springs are, then we can just do a little bit of algebra on this and figure out that work due to other forces, these other forces, it's things like friction, for example. Friction is one of the most common other forces, or just some outside applied force. This work other is often friction, and it is equal to the change in kinetic energy plus the change in gravitational potential energy. Gravitational potential energy is from the force of gravity. The change in gravitational potential energy is equal to the mass of an object times the acceleration due to gravity, 9.8 meters per second squared, times the change in height. And it is very important to note here that g is a positive number. If we have a positive mass and a positive change in height, if delta y is positive, that should mean that we've given something gravitational potential energy because it has more potential to fall down. If we have a positive gravity, positive acceleration due to gravity, then altogether we've got a positive change in gravitational potential. If we've got a negative gravity, that means that an object going up somehow lost the potential to fall down, which doesn't make much sense. And you all also see this equation in this form, UG is equal to mgh. That's pretty common. H is height, y is, y position. It's the same thing. Sometimes we could use d for distance. It just means that something is some vertical height up. We need to set an origin point at which the gravitational potential energy is equal to 0. And we can set this to be anywhere in the universe that we want. So we should try to pick something convenient. Potential energy, any kind of potential energy, especially in this case gravitational potential energy, is relative to something. Gravitational potential does not have some absolute amount generally. It's just if you move something around, it might have more or less than it does at other places. In effect, this means that we need to just set somewhere for y to equal 0, or height to equal 0, and then we'll just say, yeah, the gravitational potential energy at that point is 0. At that height, whatever we define to be 0, gravitational potential will be 0 there. That could be the floor, for example, or sea level, or the top of a table if everything is happening on a table, or the bottom of a table if something is falling off a table. Anything like that, wherever is convenient. And it doesn't really matter where we set it, as long as we're consistent with it. Let's do a quick example. Determine the change in potential energy of a 2-kilogram block, or book, as it falls 1 meter from the top of the table to the ground. Take the ground to be y equals 0 meters. Question, does it gain or lose potential energy as it falls? And remember, we are determining the change in potential energy of that book. I give you this equation, UG is equal to mgy. We have a table and a book, and the book is going to fall off the table. We have defined the floor to be h equals 0 or y equals 0, however we want to talk about it. The book goes back and forth, and different classes will go back and forth, so get used to different kinds of notation. We can say that the change in gravitational potential energy, the G means gravitational, the U, for some reason, means potential. So change in gravitational potential is equal to, well, delta, change in, is final minus initial. So I've got the UG final minus UG initial there. I can plug in the corresponding equation. So the gravitational potential final is going to equal the mass, which doesn't change, so I don't need to do initial and final on mass, times the acceleration due to gravity, which also doesn't change, there's no initial and final, times the height, or y, whichever letter you want to use, and that does change. There's a final and there's an initial. You can do some algebra on that if you wish, but you don't necessarily have to. The final height is 0 because it hits the floor, and so that term goes to 0, and you just get negative the mass, 2, times the acceleration, 9.8, times the height initial, which is 1, because it started off at a height of 1 meter. You plug that into your calculator, you get that it was negative 19.6 joules. That's this version of the problem, but there's another version. Now we're going to take the top of the table to be h equals 0. Instead of the floor being h equals 0, now the top of the table will be h equals 0. We can redraw that here. The top of the table is now h equals 0. Down here at the floor, that's actually going to be a height of negative 1 meter, because if that's 0 up there, then down here is going to be negative 1. We have the same thing here, no change there. We've got the same thing there, no change there. Here we have a change. The height final is negative 1. 2 times 9.8 minus 2 times 9.8 times the initial height, which was 0 because it was initially at 0. And you get the change in gravitational potential being the same number, negative 19.6 joules in both cases. It's the same. That's very convenient for us because that means that we can set h equals 0 to be wherever we want it to be. We don't have to set it at the floor. We could set it at the table. We could set it at the roof. We could set it at sea level. We could set it at the surface of the moon for all we cared. We can set h equals 0 to be anywhere. But as long as we're consistent, as long as we keep it there the whole problem, then everything is fine. Now we can discuss more of conservation of energy. If we look back to the work-energy theorem, we remember that work total is equal to change in kinetic energy, and the gravitational work, the work due to gravity plus the work due to springs, plus the work due to anything else that we can list off, like friction, is going to be equal to the change in kinetic energy. And as I already showed you, the work due to gravity is equal to the negative of the change of the gravitational potential energy. We're ignoring springs, so we can say that the work done by other forces is equal to the change in kinetic energy plus the change in gravitational potential energy, with the others being friction or an external push or something else. We have a special name for the change in kinetic energy plus the change in gravitational potential energy. Really, this is the change in all, or the total amount of all of the different kinds of kinetic energies plus all the different kinds of potential energies. But this is all that we've talked about so far. And this is the change in the total mechanical energy. This is what we very, very often use in these kinds of questions. And you see the result down here, that the work due to other forces is equal to the change in the, what we're just going to call the total energy of a system. The work due to other forces is equal to the change in energy of the system. This is that famous conservation of energy equation. If you've ever done conservation of energy before in high school or some such, then you have probably seen some variant of this, that the change in energy is equal to the work done on the system by a variety of different forces, only a few of which we'll actually talk about. The change in energy in a problem, sometimes it's 0. If there's no work being done outside, like friction or a push, there's no other types of work other than the things that we're going to specifically come up with an equation for, then the work other is 0, and so the change in energy is 0. And so often we'll have an equation that looks like this. The change in energy is just equal to 0. And the change in energy is equal to the, well, change in, that's final minus initial. So E final minus E initial is equal to 0. And therefore we get an equation that often, but not always, looks like energy initial is equal to energy final. If there's no other kinds of work being done, if there's no other kinds of forces acting on the problem, then you can say that the initial energy is equal to the final energy. The problem is deciding, are there other forces acting on the system besides gravity and, well, we'll talk about springs eventually. The energies, initial and final energy, you need to take all the different kinds of energy that you have in the problem and look at what they are at the beginning, add them all up, that becomes the initial energy. Look at what they all are at the end of the problem, add them up, that becomes the final energy. We really only know 2 types of energy right now. It's gravitational potential and kinetic energy. We will cover springs very soon, tomorrow most likely. And that'll be your 3rd thing that you can add to this. There are 2 different ways to think about delta E, and I've listed them all off here. This looks a lot worse than it really is. It's not actually as bad as it looks here. So let's step through it quickly. If I say that delta E is equal to work, I can break up delta E, which is the change in the total energy. I can break that up into the changes in the types of energy. So instead of delta E, I can say delta KE plus delta UG. So you can think about it as, if I've got 2 bank accounts, and one of my bank accounts is called kinetic energy, and my other bank account is called gravitational potential energy. If I move money back and forth between the 2 bank accounts, that should not change my net worth. That should not change how much money I have total just by moving money back and forth between bank accounts. That's what this is saying. If I move energy from one type of energy to another type of energy, it shouldn't actually change the total energy. Only if I do work will I change my energy. Now, this is a funny kind of way of using this as an example. The only way that I can change my bank account is by doing work as well. Like right now, I'm doing work, and so that's changing my bank account. In physics terms, doing physics work is the only way of changing your energy. And that can either go into one account, your kinetic energy, or a different account, your gravitational potential energy. You can break each of these deltas into their final minus initials. So delta kinetic energy might be kinetic energy final minus kinetic energy initial. Change in gravitational potential would be final minus initial again. However, there might be some problem where you're told directly, oh, the change in gravitational potential, it's 19 joules. I don't know. You might be told in a problem exactly, yeah, the change in this thing is going to equal that. And if that's true, then you don't need to break it up. If you're told the change in gravitational is 19 joules, then you don't have to break it up into UG final minus UG initial. You can leave it as just 19 joules right there. And then solve for whatever else you need to solve for. That's not always going to be the case, of course. So if the work from outside is 0, we can set W equal to 0, and then do a little bit of algebra on it, and you put all the initials on one side, all the finals on the other side. You've got initial kinetic plus initial gravitational potential is equal to kinetic final plus kinetic, or plus a gravitational potential final. On the other hand, there's a different way of doing this. You start with the same equation, delta E is equal to W. You can, instead of breaking delta E into its different kinds of energies, you can break it up into final minus initial is equal to work. Energy final minus energy initial is equal to work. Then you replace your energy final with kinetic energy final plus gravitational potential energy final, because those are the two types of energies that we've discussed, minus energy initial. Well, that's going to be the kinetic energy initial and the gravitational potential energy initial. Notice that I've distributed the negative sign to both of these. This negative sign here has now gone to both of these terms because you have to do that with algebra. If you set work is equal to 0, then you rearrange just a little bit and do just a little bit of algebra, and you get the exact same equation that you got before. You can think of this in either of these terms, looking at the breaking up delta E into its different kinds of energies, or breaking up delta E into final minus initial and working from there. Say that you know that the final energy is 0. If you know that, we'll do a problem later on today with an object that you push across the floor, and then friction, after you let it go, friction will make it come to a stop. It ends up with no final energy. And so you can just say, well, my final energy is 0, and you can just plug that in there. So depending on your situation, you might want to use one of these methods or the other, and we will switch back and forth between these methods just to do whatever is the most convenient for solving a problem. Let's do an example of this. I fire a cannon from the top of my 18.5 meter castle. The cannonball is shot at 130 meters per second. How fast is it going when it hits the water below? We had a very similar problem when we were doing kinematics, and the question was, how far away is it? And you can figure that out with kinematics. I also assigned you a homework question where you're supposed to find out how fast it's going when it hits the water below. And that's kind of a tough homework question. You had to do quite a bit of trigonometry, and you had to use Pythagorean theorem and all that to figure this out. But I'm going to show you that you can figure this out a lot faster using energy than you can with kinematics. We've got our 18.5 meter tall castle. We've got the cannonball being fired out at 130 meters per second. It hits the water at some final speed. I have decided to set y equals 0 to be the water. I wasn't told to do that in the problem, but as we demonstrated before, we can kind of set it wherever we want. We could set it to be where the cannon is. We could set that to be y equals 0. But why not just that? Like, we could do things like, yeah, let's set it halfway in between. That's y equals 0. That's not very smart. We could set it to be, you know, way, way, way up high somewhere. That's also not very smart. We could set it to be the center of the Earth. That's not very smart. Let's just set it somewhere convenient, like sea level. Well, that works. We start by saying delta E is equal to the work done by other forces. Are there other forces in this? Well, okay, let's see. What are our forces that usually go into work? It's things like gravitational force. But we already made an account for that. That's not part of other, that's part of the total work. We're including the effect due to gravity in our delta E. Are there any springs in this? No. And we haven't even talked about springs yet. All we've talked about is kinetic and gravitational potential energies. So there's nothing else to put in work other. There's no friction. We're going to assume there's no friction because we have not talked about drag in sufficient detail to be able to do this with drag. So I can say that energy final minus energy initial from there is equal to 0 because work other is equal to 0. I can then break my final energy into kinetic energy final plus gravitational potential energy final, and my energy initial into kinetic energy initial and gravitational potential energy initial. Notice that I distributed the negative sign there because I have to. My final gravitational potential energy, well, that's going to be 0. It ends up at a height of 0. And if y is 0, then mgy is 0. So I know that I will have no gravitational potential energy at the end of the problem. That's a good thing to remember and to be able to say, oh yeah, I know that's going to be 0, so I can just cross it out preemptively. What do we do from there? Well, we say kinetic energy final. We do a little bit of algebra and we say is equal to kinetic energy initial plus gravitational potential energy initial. This algebra right there, that's optional. You don't have to do that. I just like seeing it more like this. because I don't have to make sure, I've gotten rid of the negative signs. That's really it. I can then plug in the equations that I know, 1/2 mv squared for kinetic energy, 1/2 mv squared for kinetic energy. Notice that I have final and initial there and there. That plus the mass times the gravity times the y initial from gravitational potential energy initial. I can then plug in all of my numbers. Oh, actually, I do a little bit more algebra first. I solve for v final squared, and then I can plug in my numbers. V final squared is equal to 2 times 1/2 times 130, the initial velocity. Notice that there's no x and y here. Energy does not care about x and y. It's just 130 squared plus 9.8 times 18.5. That's my y initial. If my y final is 0 down here, then my y initial was 18.5 up here. My 9.8 is positive because we always list G as being positive. We solve for V final, we get 131.4 meters per second. Did I multiply both sides by 2 over m? It looks like I did. Yes. It looks like I factored out the m's, and so I divided up both sides by m, and then I multiplied both sides by 2, it looks like, yeah. Here's another example. I toss a pencil at the ceiling. I'm sitting in my chair and I toss a pencil at the ceiling because why not? The pencil hits the ceiling at 3.1 meters per second. Remember, this is like my example of punching me in the face. Yeah, your fist will stop eventually, but that wouldn't work in a court of law because, it was not going at 0 speed when it hit my face. Similarly, the pencil is not going at 0 speed when it hits the ceiling. It will stop, but it does not hit at 0 speed. The ceiling is 2.5 meters above the floor, but I'm throwing it from 0.9 meters above the floor. I'm just sitting in my chair, and I throw it from sitting in my chair 0.9 meters above the floor. Find the change in height, or the questions to think about. Think about finding the change in height of the pencil, how you do that. Think about the initial velocity, how you'd find the initial velocity of the pencil. And should the mass of the pencil actually matter? And hint, it's not going to, just like last time. These are just questions to think about every time you do one of these problems. The question that I actually want answered is, what is the initial speed of the pencil? How fast did I throw the pencil? Notice, if you've taken physics in high school, for example, I've seen a lot of people that just say something like, kinetic energy is equal to gravitational potential. That's not going to work here. That is not going to be enough here to solve this problem. So I want you to be careful when you are doing this kind of problem and actually go through it step by step as we're doing now. I have everything set up here. Again, final velocity was 3.1 meters per second when it hits the ceiling. The final height is 2.5 meters because that's how high up it is up there. The initial height was 0.9 meters and the floor is 0 meters. I've decided, because why not, we can set the height of the floor to be 0 meters. We want to find the initial velocity. The work done by other forces is equal to the change in energy. There are no other forces because really, okay, we haven't really talked about any other than friction. And I have not given you an example with friction yet, so we're not going to have anything right there. We will by the end of the day. We'll have friction going in right there. But that's equal to delta E. There's nothing over here, so delta E is equal to 0. This time I'm going to say that delta E is equal to the change in kinetic energy plus the change in gravitational potential energy, and that's equal to 0. I can break it up into all the different components. Change in kinetic energy is kinetic energy final minus kinetic energy initial plus gravitational potential energy final minus gravitational potential energy initial. That's delta UG, all equal to 0. Plug in all those equations. We know kinetic energy is 1/2 mv squared. Gravitational potential is mgy. Keep the subscripts right, initials, finals, etc. We can cancel out m everywhere. There's an m in every term. We can divide both sides by m. 0 divided by m is still 0. All these take the m out. We know the initial conditions. The final velocity is 2.5 meters. The final height is, the final velocity is not 2.5 meters. It's 3.1 meters per second, excuse me. Final height is 2.5 meters. Initial height was 0.9 meters. Initial velocity is what we're looking for. You plug everything in into there, canceling out the m, and you can find that the initial velocity must have been 6.4 meters per second. Yeah, mass is irrelevant in this. Looking at this, we can factor m out of every single term, and that would end up giving us m times 1/2 v final squared minus 1/2 v initial squared plus mass plus gy minus gy. You can factor m out of the entire thing. If you divide both sides by m, then the m goes away on this side, and it's 0 divided by m over there, but 0 divided by m is still 0. So the mass did not matter here. If you want to throw something at the ceiling, if you're 0.9 meters above the floor, and the ceiling is 2.5 meters above the floor, and you want something to hit at 3.1 meters per second, no matter how heavy it is, you need to throw it at 6.4 meters per second. And that works. You can try that out yourself. 2 objects thrown at the same initial velocity will reach the same height. It's the same principle as taking a heavy object and a light object and dropping them. They drop at the same rate. Throwing them, if you threw them at the same velocity, then they'd reach the same height. Mass is irrelevant in a lot of these questions, and then we'll get to springs, and it's relevant again when we get to springs, annoyingly. A skateboarder coasts at 8 meters per second on flat ground, then encounters a long ramp. How high does she get on that ramp if she just coasts? I've drawn up the setup. We've got the skateboarder. Initial velocity 8 meters per second. Goes up this ramp. If we set the height, the y initial, to be 0 down there at the bottom of the ramp, we need to find out how high up she goes, or the height final there. We're not looking for this linear distance. We're just looking for that vertical distance right there. We do not need that angle in there. We don't have to have that angle in there to solve this problem. That's also really neat in this kind of question. Energy really simplifies a lot of things. We start just the way that we've been starting. Delta E is equal to work other. We haven't even talked about any other kinds of work other than friction, which we will get to shortly. Energy final minus energy initial is equal to 0. Energy initial is equal to energy final, just doing some algebra on that. You can say kinetic energy initial plus gravitational potential energy initial is equal to kinetic energy final plus gravitational potential energy final. Well, if she starts down here, her height is 0. Gravitational potential energy initially is 0 at that point. And I'm asking, so we can just cross that out right there. I'm asking, how high up does she go? Well, when she's done going up the ramp, she stops. And when she stops, her kinetic energy is 0. So kinetic energy final must be 0. And so I've eliminated both of these terms right there, which simplifies things a bit. I've got kinetic energy initial is equal to gravitational potential energy final. I can give you the equations there. I can divide both sides by m. Here, it's probably easier to see how I can get rid of m so readily on so many of these problems. I've got 1/2 mv squared is equal to mgh, and I can just divide both sides by m, and it goes out automatically. And then you plug in all the numbers that you've got, and you get 3.27 meters. Starting off at 8 meters per second, you'd go 3.27 meters high on this. which isn't bad. 8 meters per second is like 17 miles per hour, and 3.27 meters is like 10 feet. So it's going up like one floor worth of ramp, starting off at 17 miles per hour, 18 miles per hour, something like that. Now, we've finally got one with friction as work. I shove a box across a mostly smooth floor at 2 meters per second. So I'm pushing it across the floor at 2 meters per second, but then I let it go, and I'm not pushing it anymore. Well, it's eventually going to stop. It's not going to stop immediately when I let it go. I've given it some initial velocity, and so it's going to go for a little bit, but then it's going to stop because of friction. So I wait for it to slow down and stop. Imagine taking one of those rolling chairs and pushing it across the ground. You can get it up to speed, and then you let go, and it still coasts across the room for a little bit before actually stopping. The coefficient of friction, of kinetic friction, is 0.15. That's not a very large number. 1 is a large number. 0.15 is a pretty small number. So this is a pretty low friction kind of floor. Question, are there any external forces acting on the box after I let it go? Are there any other forces acting on it, using the terminology? Yes, there is the work due to friction on this. Will that provide work on the system? Yes. I've got the block. I've got the friction, 0.15. I'm looking for the distance that it'll take to stop. Got the initial velocity of 2 meters per second. I start with the equation delta E is equal to other work. Well, we finally have it. We finally have something to plug in here. It's friction, the work due to friction. We already talked about the work due to friction when we talked about another example of a block on a floor, or a box on a floor, I believe. We talked about it last time, and we found that the work due to friction is negative, which totally makes sense because work is the energy you're adding to a system. If you are adding energy to something, then you're doing positive work. But if you're taking away that energy, then you're doing negative work, and friction takes energy away. I can say that delta E is E final minus E initial. And I remember from last time that work is equal to the force times the distance times the cosine of the angle between the force and the distance. Notice that in this problem, there's not going to be any kind of change of gravitational potential. We can set y to be 0 wherever we want, as always, but if we just set y to be 0 there, then it never has any gravitational potential because it never goes up, it never goes down, it just stays right there. So we can actually completely ignore gravitational potential right here. So all the energy that we're talking about in this case is the kinetic energy. Kinetic energy final minus kinetic energy initial. See, I took the energy final and I said, what are all the things that create energy at the end of the problem? My only option is kinetic. And actually, it stops. So the kinetic energy final is about to be 0. You'll see that very soon, the final kinetic energy will be 0. Anyway, initial energy is definitely all kinetic. And it was initially going at 2 meters per second that way, so the initial energy is just kinetic energy. I've set y equals 0 to be wherever the box is at, and so there's no gravitational potential. The force of friction is mu times n. We keep d right there. D, by the way, is how far that force of friction is being applied. If friction was being applied over a very short period of, or a very short distance, then you'd have a very short distance there. If friction is applied over a very long distance, then you'd have a very long distance right there. That d is how far it's being affected by friction. The physical length that it's being affected by friction, which is also how far it needs to go before it stops. That d is really referencing how far, what the distance is that it's experiencing friction but that is functionally the exact same as the distance that it goes before it stops. Theta. Theta is the angle between the force of friction, which is that way, and the direction of motion, which is that way. And the angle between this and this is 180. Cosine of 180 is -1. I can say that the kinetic energy final is 0. So I've just got negative kinetic energy initial is equal to mu times n times d with that negative sign from cosine of theta. I plug in 1/2 mv squared for kinetic energy. Oh, I got rid of the negatives, by the way. I multiplied both sides by -1, so that's why the negative signs are gone. 1/2 m v initial squared is equal to mu times m times g times d. mg, where did I get that? Well, that's just the normal force. There's no weird stuff going on here, and no one pushing down on this or anything like that. So the normal force is just mg. I plug in, I cancel out the m's because there's an m on both sides. I can just divide both sides by m. And I plug in the numbers that I know, and d is the only thing I don't. I solve for that, and I find the box slides 1.36 meters before coming to a stop. Here's some other questions that I included on this slide to just help you to think about what's going on. Is the work due to friction positive or negative? Well, it has to be negative because it's removing energy. Is there any change in gravitational? No. Is there any change in kinetic? Definitely yes, it loses all of its kinetic. Question, why is there no UG and why is the final kinetic energy 0? You can see that this box, well, it's just there. Let me make this more clear. I'm going to set y equals 0 meters to be there. And so the box is at y equals 0. The equation for gravitational potential is mgh, or mgy. I keep going back and forth on that being y or h because the book keeps going back and forth on it being y or h. But if the box or block starts at y equals 0 and ends at y equals 0, then mgy or mgh is always just 0. You never have any gravitational potential. So why bother confusing yourself by including gravitational potential in here if it's always just going to be 0? Imagine, we could totally do that. We could say, instead, kinetic energy final plus UG final, gravitational potential final, minus kinetic energy initial minus UG initial. Well, that's 0 and that's 0 because it's always just at mgy, but y is 0 the whole time. So just say 0 the whole time, and you immediately just get the original that equation that we had there. Your other equation, there. Your other question, why was the final kinetic energy 0? Yeah, the question was, how far does it go before it stops? How far does it slide before it stops? If it stops, then it has no kinetic energy anymore. If the box stops, then its speed is 0, and if its speed is 0, it has no kinetic energy, because kinetic energy is 1/2 mv squared, and if v is 0, then kinetic energy is 0.